Hey guys, welcome back to another tutorial, and in this tutorial I'm going to be talking about how to make a neural network from scratch, and I'm going to be making it in JavaScript just because that's the programming language which I use on the channel, but you can basically make it in any programming language because I'm going to be explaining the concepts as well. So basically in this first part of the tutorial I'm just going to be explaining the basic concept of a neural network, what it is and how it works. So you might have heard of neural networks before. They usually talk about with like AI and stuff, and I've just used some a paint drawing website, Clecky.com, but you would have heard about neural networks being talked about with AI and stuff, and that makes it seem all fancy and things, but it's actually quite easy and very simple to understand and work with. So I'm going to be explaining the basics of how a neural network works, then I'm going to be explaining like how it learns, and then I'm going to be explaining how to build it, like physically, or not physically, but actually implement it through the rest of this series. So let's just rub out all of this, and let me make a quick sketch of what a neural network looks like. So I'm going to have red, let's just have something like this, so I'll just have 80. Okay, so a neural network is basically a network of nodes and weights which connect together to create a sort of function, like a very complicated function which is going to predict certain outputs. So here we have our first layer. Now I'm going to create a second layer using some blue dots, and finally I'm going to create a output layer using some green dots. Oh, actually, let's use different shade of green. Okay, so what this represents is each dot represents a node in the network. So for example, these two actually represent the input neurons. So for example, since there's two of them, we could be inputting something like a coordinate, like 5, 3 something, and you'd input these into a coordinate, and then what happens is this neuron is connected to every single other neuron in the next layer. Same for this, but I'm not going to draw it. And then each layer in this neuron is connected to every layer in the next neuron, like that, and it gets passed along. So if we input let's input a 5 here and a 3 here, what's going to happen is it's going to get passed along along these weights, which are these black lines connecting each one are actually called weights, or sometimes synapses, and yeah, they get passed through this network, and you actually end up with an output. So this output is usually a binary choice. It's either going to be like usually 1s and 0s, and basically what we're trying to train our network to do is, let's say we had a collection of points, let's just make up some new ones, 4, 6, dot dot dot. You're going to input all of these points in, and you're expecting to get some outputs. So for example, for 5, 3 you'd expect 1, 0, and for 4, 6 you'd expect 0, 1, something like that. And if you were to plot these points on a graph, so we have 5, 3 here, and 4, 6, which is going to be here, we could do something like, we want it to separate out the points like this. So on this side we would like the neuron to classify these points as being 1, 0, whereas the points on this side we'd like it to classify them as being 0, 1, like so. So yeah, that's basically how it works. You basically give it some inputs and tell it the expected output, and you want to make it learn, adjust these weights, and basically create itself. Just keep learning until the accuracy comes down to a suitable level. So we've already mentioned that these are nodes and they store values, but what I haven't talked about yet is these weights. These weights are actually just multiples. So for example, this could be multiplied by 3, this one could be multiplied by 0.7, something like that, and you can see 5 go into this, so now the 5 would get turned into 15 here, but you'd also have to include the product of 3 multiplied by this weight, which is going to give that, so it's going to be 15 plus whatever this is. And yeah, that's how you calculate the values for the next neuron. Then you do the same for all of these, and these weights are basically act as a multiplier, which allow you to gets sort of biased data, which is what's going to enable you to get functions which can classify things. Now, one final thing I haven't talked about, actually there's two things. The first thing being biases. So these are just like, for this individual neuron we could have a bias of +1, and for this one we could have something like -7. Basically what that allows us to do is get something which is still linear but not exactly going through the origin. So for example, for this example we might want it to separate points out like this, which wouldn't be possible, since if you think about it mathematically, you're entering a number and you're only multiplying it. So if your original number was 0, it's not actually going to go anywhere apart from that, which is where these biases come in. These are just pluses and minuses rather than multiplying. So yeah, this is what biases do. Well, yeah, let's just not write it like that. But yeah, and then finally the last thing I have to talk about is activation functions. So let's do this in a different color. Let's do something like this. And yeah, an activation function basically introduces non-linearity. So let's go back to a size 4, and I'll just rub this out for now. So what I mean by non-linearity is that it's going to be able to do things like this. So let's say we want to classify all points over here being blue, all points in this region being blue, then all points in this region over here, we want these to also be blue, like this, and then all other points we want to be red, like this. So obviously, if you're just going to have basic weights and biases neural network without any activation function, then this is basically not going to be possible. The activation function is what enables you to get non-linearity in your results. And an activation function, what I mean by that is simply just a function which returns a non-linear value. So example of this could be the sigmoid function, or even just the hyperbolic tan. So if you know about mathematics, you know the hyperbolic tan function is actually going to look something like this. So let's just draw a graph. This is what it's going to look like. I believe it's something like this, so it comes in like so. And yeah, what this allows you to do is it comes in and it's not linear and it gets like distorted and then it's out. So if you imagine, we could have something like this where we just have activation there. Oh, that's actually the sigmoid, which is similar but not the same thing, but same for our purposes. So before they get converted into these node values, they go through this activation function which introduces non-linearity. So yeah, that's basically it. Now this goes through the network, and what happens is the numbers keep adding up and eventually you get to your result, which is going to come out something like this. Obviously this isn't the perfect result. Usually what happens is at first you're going to get something looking really silly like 0.5 and 0.4 or something like that, you know, something which is like nothing related to this result. But what you do with that is you actually create a cost function. So here's our expected output, here's our actual output, and we can create a cost function by finding the difference of these, then squaring them. So this would be 0.25, this would be 0.36, and then we just add up the sum. So the overall cost for this network would be 0.61, and of course we'd have to repeat this over many different data points, but this is the basic cost for our one iteration of this. Now to fix this, all you'd have to do is, this cost is just a function, right? It's just the square root of the difference of the expected outputs minus the actual outputs, sum of all of those. So that's just a function. Now we can actually just use that function. Now there's many different ways of improving the cost function, but one of the most popular is backpropagation, in which you use calculus. So if you think about the cost just being a function, then you can also think about getting all of these values as functions as well. And you basically use the chain rule to go back and get the weights which would be required for that. However, that's quite complicated, so what I'm actually going to start out with is something very simple. All we're going to do is, let me just write out all of this stuff, and this is our cost function, right? So we have C, and it takes in all of this stuff, and it gives out 0.61. So if we imagine our cost function being on a 2D graph, obviously this isn't going to be what it's like, because it's going to take all of these as inputs, but we take all of this on a 2D graph, and let's just say it looks something like this. So we have something like that, right? And you can see if our 0.61 was over here, that would probably be somewhere around here, so let's just mark that on. Okay, oh, actually that's not a good color. Right, so this is where our 0.61 would be, and what we want to do is we want to reduce this cost, right? Because a low cost means that we have accurate results, so we want to probably bring the cost around here somewhere. So what we can do is we can actually find the gradient at this point, which is quite simple using finite derivatives. I'll explain what that is in a later video, you don't really need to know about it now, but yeah, we can find the gradient of the curve here, and you can see this slope basically tells us which direction to go to move this cost function down. So if we imagine this is a cost function in like isolation with one of these weights, if we reduce this weight, the cost function is going to go to here. If we increase this weight, the cost function is going to go over to here. So we want to reduce it until we eventually get to this point, until which is going to start going up, then come back down, and it's going to start fluctuating, which tells us we've reached the bottom. Now obviously this is a global minimum. If we were to somewhere be over here, then we'd only reach here, and this is a local minimum, still a minimum, but it's not going to be as low as this cost, so that's one of the issues. But yeah, that's pretty simple. That's pretty much it to do with neural networks. Like that was quite complicated, so it's quite difficult to explain the entire thing in such a short amount of time, but hopefully I've done a decent enough job that now I can go on to the next parts of the tutorial and implement it, and you'll have an idea of what I mean. So thanks for watching, and I'll see you guys in a future tutorial. Bye!